What if everything we thought we knew about traveling across the cosmos was just the beginning? Picture a tunnel carved into the very fabric of space and time, a shortcut through the universe so powerful it could take us from one corner of existence to another in the blink of an eye. Wormholes, those cosmic bridges whispered about in physics papers and science fiction, might not be just theoretical anymore. For decades, they existed as mathematical curiosities, scribbled in the margins of Einstein's equations. But today, we stand on the edge of something extraordinary, the tantalizing possibility that humanity's first journey through a wormhole could be closer than we ever imagined. This isn't just about bending the rules of physics, it's about rewriting them. Imagine stepping through a gateway to another star system, another galaxy, or even another era. The implications are staggering: colonizing distant worlds, meeting civilizations light years away, or glimpsing the birth of the universe itself. But here's the catch: wormholes are enigmatic, unpredictable, and shrouded in mystery. They could be our greatest triumph or our most perilous gamble, and that's where the real intrigue begins. Scientists have spent generations wrestling with the puzzles they present, crafting theories that range from the brilliantly plausible to the wildly speculative. Some suggest wormholes are natural cosmic arteries woven into space since the dawn of time. Others argue they could be artificial constructs engineered by civilizations far beyond our own. So how close are we to cracking the code? That's exactly what we're diving into today. Over 30 groundbreaking theories, each one a piece of the puzzle waiting to be explored. From the mind-bending physics that could stabilize a wormhole to the terrifying risks of traversing one, we're about to embark on a journey through the most daring ideas in astrophysics. Buckle up. By the end of this, you might just find yourself seeing the universe and our place in it in a whole new light. The story of wormholes begins not with wild speculation, but with pencil marks on a chalkboard, the quiet work of two physicists reshaping our understanding of reality. In 1935, Albert Einstein and Nathan Rosen peered into the equations of general relativity and found something astonishing. Hidden within the numbers was a cosmic backdoor, a theoretical tunnel linking two distant points in spacetime. They called it an Einstein-Rosen Bridge, a structure so elegant yet so perplexing it would haunt physicists for decades. At its core, their discovery revealed how spacetime, the very fabric of the universe, isn't rigid and unchanging. Imagine a bedsheet stretched tight with a heavy bowling ball placed in the center. The sheet curves under the weight, just as spacetime warps around massive objects like stars or black holes. Now picture pinching two distant points of that sheet together until they nearly touch. That's the essence of an Einstein-Rosen bridge, a shortcut forged by gravity's relentless pull. The math suggested that under extreme conditions, spacetime could fold in on itself, creating a passage between locations that might otherwise take billions of years to cross. But here's where things get thorny. These early wormholes were more like cosmic mirages than practical highways. The equations showed them snapping shut the instant anything tried to pass through, crushed by their own instability. Some physicists compared them to a soap bubble, beautiful, delicate, and vanishing before you could reach out. Yet that fragility didn't diminish their significance. The very idea that spacetime could be threaded like a needle opened doors to questions we're still wrestling with today. Could these bridges be stabilized? Might they exist naturally, woven into the universe like invisible seams? What's striking is how Einstein and Rosen's work, born from pure mathematics, collided with the wildest frontiers of imagination. They gave us the first glimpse of a universe far stranger than we dared to dream, one where distance and time might not be the rigid rulers we once believed. And though their bridges remained theoretical, they ignited a quest that would span generations. The hunt for stable wormholes had begun. Imagine a wormhole you could actually walk through, not a fleeting mathematical quirk, but a stable, engineered passage through the cosmos. That's exactly what physicists Michael Morris and Kip Thorne set out to theorize in 1988. Building on Einstein and Rosen's foundation, they asked a revolutionary question: what if we could design a wormhole that didn't collapse? Their answer redefined the boundaries of theoretical physics. The Morris-Thorne wormhole wasn't just a cosmic curiosity, it was a blueprint for interstellar travel. At the heart of their design lies a mind-bending ingredient: exotic matter. Not the kind you'd find in a lab or even floating in space, but a hypothetical substance with negative energy density. Picture matter that doesn't just resist gravity but repels it, pushing spacetime outward like an anti-gravity force field. This exotic matter would line the throat of the wormhole, acting as scaffolding to keep it propped open against the crushing weight of spacetime's natural tendency to snap shut. Without it, traversing a wormhole would be like trying to sprint across a bridge made of tissue paper, doomed from the first step. But here's where things get even stranger. Exotic matter isn't just rare, it defies the known laws of physics. According to general relativity, matter with negative energy density could exist, but we've never observed it naturally. Some theories suggest it might manifest as quantum fluctuations, tiny, fleeting particles that pop in and out of existence in the vacuum of space. Others propose it could be manufactured through advanced technology far beyond our current capabilities. The sheer audacity of Morris and Thorne's idea lies in this paradox. To build a bridge across the universe, we might first need to invent the very materials that make it possible. What makes their work so groundbreaking is how it shifted the conversation from "are wormholes real?" to "how could we make them real?" They didn't just describe a cosmic shortcut, they gave us the mathematical toolkit to imagine stabilizing one. Their equations suggested that with enough exotic matter and a civilization advanced enough to harness it, humanity could theoretically construct wormholes like engineers build tunnels through mountains. The implications are dizzying. A Morris-Thorne wormhole could link Earth to Alpha Centauri, or even a galaxy a billion light-years away, turning journeys that would take lifetimes into afternoon strolls. Yet for all its brilliance, their theory leaves us with tantalizing gaps. How much exotic matter would we need? Could we ever produce or collect it in sufficient quantities? And perhaps most hauntingly, what happens if something goes wrong mid-journey? The Morris-Thorne model is a masterpiece of theoretical physics, but it's also a reminder that the universe doesn't give up its secrets easily. Every answer spawns new questions, and every breakthrough reveals fresh mysteries waiting to be solved. Quantum entanglement, one of the most baffling phenomena in physics, might hold the key to unlocking wormholes on a microscopic scale. Picture two particles separated by vast distances, yet instantly influencing each other's states as if connected by an invisible thread. Einstein famously called this spooky action at a distance, but what if that spookiness was literal? Some physicists now propose that entangled particles could be linked by tiny, transient wormholes, threading through the fabric of spacetime itself. This radical idea comes from a marriage of quantum mechanics and general relativity, two theories that usually refuse to play nice. In 2013, physicists Juan Maldacena and Leonard Susskind dropped a bombshell hypothesis: entanglement and wormholes might be two sides of the same cosmic coin. They suggested that when particles become entangled, a microscopic Einstein-Rosen bridge forms between them, creating a shortcut through spacetime. Think of it like a secret tunnel in a mountain. While the surface route might take hours, the tunnel connects 2 points almost instantly. If correct, this would mean every time entanglement occurs, the universe is quietly stitching together wormholes too small to see. Recent experiments have added fuel to this speculative fire. In 2022, a team at Google's Quantum Lab observed behavior in entangled particles that eerily resembled what wormhole dynamics might look like. Using a quantum processor, they simulated conditions where information seemed to teleport between particles, a phenomenon that, in their model, could only be explained by a wormhole-like connection. Of course, this wasn't a real wormhole, it was a mathematical proxy, but the implications were staggering. If quantum systems can mimic wormhole physics, might nature be doing the same thing on a fundamental level? The catch: these hypothetical wormholes would be unimaginably small, far tinier than an atom, lasting only fractions of a second. Scaling them up to human-sized passages would require energies and technologies we can't yet fathom. But here's where it gets even wilder. Some theorists argue that if entanglement creates microscopic wormholes, advanced civilizations might learn to stabilize and expand them. Imagine weaving countless entangled pairs together, like threads in a cosmic tapestry, until the resulting wormhole is large enough to traverse. It sounds like science fiction, but the math doesn't outright forbid it. Critics, however, urge caution. Entanglement is slippery, it resists classical explanations, and invoking wormholes risks complicating an already enigmatic phenomenon. Plus, even if microscopic wormholes exist, there's no guarantee they could ever be scaled or controlled. Yet this very uncertainty is what makes the idea so electrifying. It blurs the line between quantum weirdness and cosmic engineering, suggesting that the universe's most mysterious forces might be deeply interconnected. Whether or not entanglement spawns wormholes, the mere possibility has forever changed how we view the fabric of reality. If wormholes are the universe's hidden doorways, then white holes might just be the exit's cosmic ejector seats, flinging matter and energy outward with irreversible force. The concept is as mesmerizing as it is bizarre. While black holes famously pull everything in, never letting even light escape, white holes are their theoretical opposites, regions of spacetime where nothing can enter, only explode outward. Picture a black hole running in reverse, a fountain of energy and particles erupting ceaselessly into the cosmos. Now imagine one end of a wormhole anchored to a black hole's crushing grip, while the other spills out through a white hole's furious expulsion. This pair could form the ultimate interstellar transit system, a one-way ticket across the universe. The math behind white holes traces back to the same equations that predicted black holes. Einstein's theory of general relativity allows for their existence, but unlike their dark counterparts, white holes defy observation. No telescope has ever spotted one, and for good reason: they're inherently unstable. A white hole's very nature suggests it would burst apart the moment it forms, like an overpressurized balloon. Yet if one could exist long enough to pair with a wormhole, the implications would rewrite the rules of space travel. Step into the black hole entrance, and you'd be catapulted through the wormhole's throat, only to emerge from the white hole's radiant mouth somewhere entirely new. Here's where the theory twists into something even stranger. Some physicists speculate that white holes might not just be spatial anomalies, they could be temporal ones too. If a black hole's gravity slows time to a crawl near its event horizon, a white hole's explosive output might accelerate it, pass through such a system, and you could emerge not just in another location, but in another era. The white hole wouldn't just be a place, it could be a when. This raises spine-tingling questions. Could ancient cosmic explosions we've observed in distant galaxies actually be white holes? Might the Big Bang itself, the ultimate outburst of energy, have been the universe's first white hole event? Yet for all their thrilling potential, white holes come with a daunting caveat: survival. A traveler exiting a white hole would face an environment of unimaginable violence, a maelstrom of radiation and high-energy particles blasting outward at near light speed. Shielding against such forces would require technology far beyond our grasp. Even more unsettling is the possibility that white holes might reset anything passing through them. Just as a black hole's gravity spaghettifies matter, a white hole's expulsion could shred and reconstitute it. You might arrive at your destination, but would you still be you? The white hole hypothesis forces us to confront the raw extremes of physics. It's a reminder that the universe doesn't just harbor mysteries, it thrives on them. Whether these radiant anomalies truly exist or remain locked in the realm of theory, they stretch our understanding of reality to its breaking point. And that's exactly where the next great discoveries await. When two black holes spiral toward each other in a cosmic dance, their collision doesn't just send ripples through spacetime, it might tear a hole right through it. Gravitational wave detectors like LIGO have captured the echoes of these violent mergers, revealing how these events warp the fabric of reality itself. But hidden in the math behind these collisions lies an electrifying possibility. For a fleeting moment, the sheer force of the impact could stitch together a wormhole, a transient bridge between distant corners of the universe. Think of it like punching through a sheet of paper. When two black holes merge, their immense gravity doesn't just create a deeper dent in space-time, it could puncture it entirely. The resulting gravitational waves, those ripples we've observed, might carry signatures of something even stranger, a tunnel forming in the chaos, threading through dimensions we can't yet perceive. Simulations of black hole mergers show space-time stretching to its limits, with mathematical models suggesting that under extreme conditions, the fabric of reality might not just bend, it could snap and reconnect elsewhere. The catch: these wormholes would be catastrophically unstable. Unlike the carefully engineered passages theorists like Morris-Thorne imagined, merger-born wormholes would likely collapse faster than a blink. The energy required to hold them open even momentarily would be unimaginable, equivalent to the power of entire galaxies funneled into a single point. Yet the fact that nature might spontaneously create such structures, even briefly, rewrites what we thought was possible. It hints that wormholes aren't just sci-fi fantasies or far-future engineering projects. They could be natural phenomena flashing in and out of existence in the universe's most violent events. What's truly tantalizing is how gravitational wave astronomy might one day catch proof. Advanced detectors could uncover anomalies in the ripples from black hole mergers, subtle distortions that don't match predictions. These aberrations might be the fingerprints of a wormhole's formation, a space-time shortcut born and dying in the same cosmic instant. If so, it would mean that every time two black holes collide, the universe briefly offers a glimpse of its most forbidden roads we might one day learn to travel. Cosmic strings, shimmering scars from the universe's violent birth, might be the universe's own architects of wormholes. These hypothetical filaments, thinner than a proton yet denser than a mountain range, are thought to have formed in the first moments after the Big Bang, when spacetime itself was still cooling and cracking under cosmic growing pains. Picture the aftermath of freezing water. Cracks and fissures form as the ice contracts. Now imagine that on a cosmic scale, with spacetime itself fracturing into unimaginably dense strands, each one a relic of the universe's fiery infancy. If they exist, these strings could be under our noses all along, curled into invisibility by the vastness of space, or stretched taut between galaxies like invisible tightropes. What makes cosmic strings so tantalizing is how they warp spacetime around them. Unlike black holes, which crush matter into singularities, cosmic strings twist spacetime into angular defects. Pass a spaceship around one and you wouldn't feel a pull. Instead, you'd emerge in a universe where angles don't add up the way they should. It's as if reality itself has a crease. But when two such strings cross or snap past each other at near light speeds, something extraordinary happens. The collision could pinch spacetime so violently that it punctures, forming a wormhole between the string's endpoints. Think of it like pulling two threads of a sweater so tight that the fabric between them tears open, creating a hole where there wasn't one before. The math behind this is both elegant and eerie. Calculations show that intersecting cosmic strings could generate closed time-like curves, loops in spacetime that theoretically allow time travel. Even more striking is how these wormholes wouldn't require exotic matter to stay open. The string's own gargantuan tension, millions of trillions of times stronger than steel, could act as natural scaffolding, holding the wormhole's throat open against collapse. It's a cosmic free lunch, a stable wormhole forged by the universe's own primordial machinery. Yet the devil's in the details. Cosmic strings, if they exist, would be fiendishly hard to detect. They don't emit light, and their gravitational footprint is subtle. A slight lensing of starlight here, a ghostly distortion in a galaxy cluster there. Some astronomers hunt for their signatures in the cosmic microwave background, the afterglow of the Big Bang, where strings might have left faint, jagged imprints. Others propose that if a string sliced through Earth, we'd notice clocks suddenly falling out of sync or GPS systems going haywire. So far, no such anomalies have confirmed their existence, but the search is far from over. The boldest twist: if cosmic strings do spawn wormholes, they might not be random. Advanced civilizations, perhaps long extinct, could have identified and harnessed these natural spacetime tunnels, weaving them into a galactic transit network. Imagine ancient alien engineers stabilizing string-borne wormholes with technology we can't yet fathom, turning cosmic accidents into interstellar highways. It's a dizzying thought that the universe might have pre-installed its own shortcuts, waiting for someone or something to find the keys. Of course, this is all speculation wrapped in mathematics. Cosmic strings remain one of physics' great what-ifs, but that's the thrill of it. They remind us that the universe's earliest moments might have left behind more than just stardust. They could have threaded the fabric of reality with hidden passages, dangling the ultimate prize just beyond our grasp. Whether these threads are real or not, the mere possibility reshapes how we see the cosmos, not as a static stage, but as a dynamic web of untapped potential. Stabilizing a wormhole isn't just about bending space-time, it's about defying it. And that's where negative energy enters the equation, a concept so bizarre it feels ripped from the pages of a comic book. Unlike the energy we encounter daily, the kind that powers stars, fuels our bodies, or charges our phones, negative energy flips the script. It doesn't just resist gravity, it repels it, creating a sort of anti-gravity effect that could theoretically prop open a wormhole's throat like cosmic scaffolding. Without it, even the most carefully engineered wormhole would collapse faster than a house of cards in a hurricane. But what exactly is negative energy? Picture a region of space where the energy density drops below zero, a place where empty vacuum somehow contains less than nothing. It sounds impossible, but quantum mechanics whispers that it might not be. At the tiniest scales, particles flicker in and out of existence, borrowing energy from the future in fleeting violations of the laws of physics. These quantum fluctuations can, under certain conditions, create pockets of negative energy. The catch: they're microscopic and vanish almost instantly. To stabilize a wormhole large enough for a speck of dust, let alone a spacecraft, you'd need to harness and amplify these effects on a staggering scale. The challenges don't stop there. Even if we could produce negative energy, controlling it would be like trying to bottle a thunderstorm. The Casimir effect, a lab-tested phenomenon where two uncharged metal plates placed nanometers apart in a vacuum experience an invisible pull, hints at how negative energy might be manipulated. The plates suppress certain quantum fluctuations between them, creating a relative negative energy density. But scaling this up to wormhole-sized applications would require technologies we can't yet conceive, like energy fields capable of stitching space-time itself. And then there's the elephant in the room. The laws of physics might outright forbid it. The null energy condition, a cornerstone of general relativity, suggests that negative energy on large scales could unravel causality, breaking the chain of cause and effect. Imagine a wormhole where exiting before you entered becomes possible, creating paradoxes that could make time travel look tame. Some theorists argue that the universe inherently protects itself from such violations, slamming the door on stable wormholes before they can destabilize reality. Yet the tantalizing possibility remains. If negative energy can be harnessed, perhaps through advanced quantum engineering or undiscovered cosmic phenomena, it would rewrite not just the rules of space travel, but our understanding of the universe's deepest fabric. The quest to unlock it isn't just about building shortcuts through the stars. It's about probing the very boundaries of what physics allows, and that's a frontier worth exploring, no matter how impossible it seems today. Time travel isn't just a trope of science fiction. It might be lurking in the math of wormholes. The moment you bend space-time into a tunnel, you're not just playing with distance, you're tangling with time itself. Picture a wormhole where one end stays near Earth while the other rockets away at near light speed. Thanks to Einstein's relativity, time would pass slower for the moving end. Return it to Earth after a decade, and you'd have a bridge not just between places but between eras. Step through one side, and you might emerge 5 years before you left. The universe's most audacious shortcut could double as its first time machine. But with this power comes paradox, none more infamous than the grandfather paradox. What if you traveled back and prevented your own birth? The logic unravels like a knotless thread, yet physicists aren't ready to dismiss the possibility. Some suggest the universe might enforce consistency through self-correcting events. Try to erase your grandfather, and quantum randomness or unseen forces could thwart you. A slipped bullet, a missed encounter, fate conspiring to preserve the timeline. Others propose branching realities where every choice splinters off a new universe, rendering paradoxes harmless. In one timeline, your grandfather lives. In another, he doesn't, and you're simply a visitor from a parallel thread. The wildest resolution comes from Nobel laureate Kip Thorne, who theorized that wormholes might snap shut the instant paradox-threatening feedback loops form. Imagine the wormhole as a cosmic circuit breaker, cutting power before reality shorts out. But even these elegant solutions can't mask the sheer strangeness of time travel's implications. Would information flowing backward spawn infinite loops, like a video call where each device broadcasts the other's screen? Could we receive messages from future civilizations, only to become the senders when our time catches up? Perhaps the most unsettling idea is that time travel might already exist, just not for us. Wormholes formed in the early universe, stretched by cosmic expansion, could stitch together wildly distant epochs. A civilization that stumbled upon one might see Earth's dinosaurs or its dying stars all from the same portal. Yet for now, these remain whispers in the equations. The universe keeps its secrets close, reminding us that some doors once opened might not lead back. The holographic principle turns everything we think we know about reality inside out, literally. Imagine the entire universe with its galaxies, black holes, and wormholes, not as a three-dimensional tapestry, but as a two-dimensional surface, like a cosmic DVD encoding everything in flat, intricate patterns. This mind-bending idea suggests that our perception of depth and volume might be an illusion, a projection from a lower dimensional boundary where all the true information is stored. If that's the case, wormholes could be far simpler than we've dared to imagine. Instead of engineering tunnels through sprawling 3D space, we might only need to manipulate data on this underlying 2D surface, like pressing a finger against a screen to create a ripple in the digital world above. Think of it like a hologram on a credit card. Tilt it, and the flat sticker reveals a shimmering 3D image, even though it's just light interacting with microscopic grooves. The holographic principle proposes that space-time works the same way. Every event, every particle, even our thoughts, are just projections from a deeper layer of reality. For wormholes, this could mean their daunting complexity, exotic matter, gravitational balancing acts might dissolve into a problem of information transfer. A stable wormhole wouldn't require bending space in 3 dimensions. It might just need the right codes rewritten on the universe's 2D hard drive. The implications are staggering. If the universe truly operates like a hologram, wormholes could be less about physics and more about pixels, tiny units of space-time information that, when reconfigured, open gateways. Theoretical physicist Juan Maldacén's work on anti-de Sitter space, a mathematical model of the holographic principle, showed how black holes in 3D could be described by quantum particles on a 2D boundary. Extend this to wormholes and suddenly, threading one might be akin to debugging cosmic software, finding the right algorithm to link 2 points on the surface. Critics, though, highlight the gap between theory and reality. The holographic principle remains largely untested, its math confined to idealized models of the universe. And even if it holds, simplifying wormhole creation might still demand technologies indistinguishable from magic, like a civilization that could rewrite the fabric of reality at the Planck scale. Yet the mere possibility reshapes the quest. If wormholes are holographic glitches, their secrets might not lie in the stars, but in the quantum scribbles at the edge of existence, waiting to be decoded. Dark matter, the universe's most elusive architect, might be weaving wormholes right under our noses. We know it's out there. Its gravitational fingerprints are etched into the rotations of galaxies and the bending of light around cosmic voids. But its true nature remains one of physics' greatest enigmas. What if this invisible substance, making up 85% of the universe's mass, isn't just a passive scaffold holding galaxies together? What if it's actively sculpting spacetime into hidden tunnels, creating a shadowy network of cosmic shortcuts? The idea stems from dark matter's peculiar behavior. Unlike normal matter, it doesn't emit, absorb, or reflect light, yet its gravitational influence is undeniable. Some theories suggest dark matter could consist of exotic particles that interact with spacetime in ways we've never imagined. If these particles carry unique properties, like negative mass or repulsive gravity, they might naturally warp spacetime into stable wormholes without the need for artificial stabilization. Picture a river carving underground caves over millennia. Dark matter could be doing the same to the fabric of the universe, slowly etching out passages we can't see but might one day learn to traverse. Observational clues are tantalizing. Astronomers have spotted bizarre gravitational anomalies, regions where light bends too sharply, or galaxies move as if tugged by invisible threads. Some of these could be explained by hidden concentrations of dark matter, but others hint at something stranger. In 2018, researchers studying the cosmic microwave background found faint filamentary patterns that didn't match standard models of dark matter distribution. These filaments, some speculate, might trace the outlines of wormhole throats, their gravitational shadows subtly altering the oldest light in the universe. Even more compelling are the odd orbits of stars near our galaxy's center. Some whirl around empty patches of space as if something massive, yet utterly invisible, anchors them. Traditional dark matter clumps could explain this, but alternative models suggest these might be the mouths of wormholes, their entrances cloaked by the very substance that formed them. If true, we could be living in a galaxy crisscrossed with dormant portals, their existence masked by the darkness that built them. The challenge, of course, is proving it. Detecting a dark matter wormhole would require spotting gravitational signatures unlike anything else in space. Perhaps a star that flickers as it passes through an invisible tunnel, or a pulse of radiation from particles vanishing into one end and emerging light years away. Next-generation telescopes like the Vera Rubin Observatory might soon catch these whispers in the data. Until then, the theory remains a breathtaking possibility that the universe's missing mass isn't just hiding in plain sight. It might have built the ultimate transportation system, waiting for us to decipher the map. At the smallest scales imaginable, spacetime isn't the smooth, placid surface we perceive. It's a seething, bubbling quantum foam where reality itself churns with unimaginable energy. Picture an ocean in a storm, but instead of waves, the very fabric of existence is constantly warping and reforming, creating fleeting micro-wormholes that blink in and out of existence faster than a thought. This is the quantum foam hypothesis, a radical vision of the universe where wormholes aren't rare cosmic anomalies, but as common as the particles zipping through the void. The concept traces back to physicist John Wheeler in the 1950s, who proposed that at the Planck scale, distances a trillion times smaller than an atom, spacetime becomes a chaotic froth. Quantum fluctuations, the same phenomena that allow particles to momentarily pop into existence from nothing, might also twist spacetime into tiny tunnels. These wormholes would be unimaginably small, lasting only fractions of a second, but their implications are colossal. If spacetime is fundamentally foamy, wormholes could be woven into the universe's very structure, appearing and vanishing like bubbles in boiling water. What's astonishing is how these microscopic wormholes might stitch together reality. Some theories suggest that quantum entanglement, the spooky connection between particles across vast distances, could be mediated by these fleeting spacetime tunnels. Imagine two electrons entangled, their states mysteriously linked. A Planck-scale wormhole could act as the hidden bridge between them, a shortcut through the quantum foam that explains their instantaneous correlation. It's a tantalizing idea. The universe's most bewildering phenomenon might be powered by wormholes too small to see, but here's the catch. Observing quantum foam directly is impossible with current technology. The scales involved are trillions of times beyond our most advanced instruments. Even if we could, the wormholes within it would be so unstable that any attempt to interact with them would likely collapse them instantly. Yet their existence, even as mathematical ghosts, reshapes how we think about space-time. If quantum foam is real, then wormholes aren't just rare cosmic quirks, they're part of the universe's daily rhythm, constantly forming and dissolving in the background of everything. The most mind-bending implication: if civilizations could somehow stabilize these natural wormholes even for an instant, they might unlock the ultimate hack, a space-time network built into the quantum foam itself. Imagine tapping into a froth of pre-existing tunnels, expanding them like inflating a balloon and stepping through. The universe might have already provided the roads, we just need to learn how to pave them. For now, quantum foam wormholes remain a dazzling theoretical possibility, a whisper in the equations that hints at a reality far stranger than we've dared to dream. What if the secret to wormholes lies not in our familiar three dimensions, but in hidden folds of reality we can't even perceive? String theory, the most ambitious framework in modern physics, proposes that the universe isn't just built on length, width, and height. It suggests 6 additional spatial dimensions, curled up so tightly they're invisible to us, like the intricate grooves on a vinyl record too small for the naked eye to see. These extra dimensions might be the missing ingredient that makes traversable wormholes not just possible but inevitable. Imagine space-time as a vast ocean. We're ships sailing its surface, oblivious to the currents swirling beneath. But deep below, in those compactified extra dimensions, gravity could be leaking through, creating shortcuts between distant points. A wormhole in this view wouldn't tunnel through our three-dimensional space. It might dip into a higher dimension and re-emerge elsewhere, like an ant crawling from one end of a folded napkin to the other by slipping through an unseen fold. The mind-bending implication: traveling through such a wormhole wouldn't require moving faster than light in our dimension. You'd simply be taking a detour through deeper geometry. String theory's mathematical elegance suggests how this could work. In these higher dimensions, the strings that make up all particles could vibrate in ways that stabilize wormhole throats naturally. Some models propose that when D-branes hypothetical multidimensional objects in string theory collide, they might pinch spacetime into permanent wormholes. Picture 2 sheets of paper floating parallel in air, suddenly pressed together at one point. Where they touch, a passage forms. In the extra-dimensional landscape, this could create structures far more stable than anything allowed by 4-dimensional physics. Even more compelling are the Kaluza-Klein wormholes, theoretical constructs that weave through compactified dimensions. If you've ever blown up a balloon with dots on it, you've seen how shrinking the balloon makes the dots seem closer together. Extra dimensions might work similarly, bending in ways that bring distant points into proximity when viewed from a higher dimensional perspective. A civilization that mastered navigation through these realms could essentially fold the universe at will, turning galactic voyages into neighborhood strolls. Yet for all its promise, the extra-dimensional hypothesis comes with profound challenges. We have no experimental proof these dimensions exist, let alone that they host wormholes. The energy required to probe or manipulate them might exceed anything our particle colliders can muster by billions of times. And if they do exist, their physics could be so alien that our current math is like trying to describe the internet with medieval parchment. What keeps physicists pursuing this path is the sheer explanatory power it offers. Extra dimensions could solve multiple cosmic puzzles at once. From why gravity is so weak compared to other forces, it might be diluted across dimensions, to how quantum mechanics and relativity might finally reconcile. If they also hand us the keys to wormhole travel, it would be the ultimate cosmic two-for-one deal. Until then, the idea stands as a breathtaking reminder. The universe's greatest shortcuts might be hidden in dimensions we're only beginning to imagine. Bending spacetime isn't just a wormholes game. The Alcubierre drive plays by similar rules, but with a twist that redefines what travel even means. While wormholes stitch distant points together like cosmic thread, the Alcubierre concept imagines a starship surfing on a wave of warped spacetime itself. Picture a treadmill where the fabric of reality moves beneath you, contracting space ahead while expanding it behind, so your vessel glides effortlessly faster than light, never breaking physics' speed limit locally. It's not propelling through space, it's making space do the propelling for you. The genius lies in their shared foundation, Einstein's revelation that spacetime is malleable. Both theories exploit general relativity's loopholes, but where wormholes punch through spacetime like a tunnel through a mountain, the Alcubierre drive folds the mountain's path around the traveler. One's a shortcut, the other's a moving walkway, and just like wormholes, the Alcubierre drive hinges on exotic matter with negative energy, a substance that defies conventional physics to create the necessary spacetime distortions. Without it, both ideas crumble like a sandcastle in a hurricane, yet the differences are as striking as the similarities. A wormhole is a fixed structure, a cosmic subway connecting fixed stations. The Alcubierre drive, though, is self-contained, a ship carrying its own spacetime bubble, untethered to any predefined route, need to reroute mid-journey. No problem, the flexibility comes at a cost, though. While wormholes might theoretically allow two-way travel, Alcubierre's warp bubble could trap its passengers in a one-way ride, with no guarantee of stopping gracefully on the other side. Then there's the energy problem. Stabilizing a wormhole might require the mass energy of a small star, but the Alcubierre drive could demand even more. Some calculations suggest equaling the entirety of Jupiter's mass converted to exotic fuel. Yet recent tweaks to the math hint at workarounds, like oscillating warp fields that slash energy needs. It's a reminder that both theories are works in progress, each refining the other's possibilities. What makes these ideas complementary is their shared audacity. They're not just about going faster, they're about reimagining movement itself. A wormhole rewrites the map. The Alcubierre drive rewrites the rules of the road. And somewhere in the interplay between them, humanity might just find the key to stepping beyond the confines of our cosmic neighborhood. What if the universe's most infamous cosmic traps, black holes, aren't what they seem at all? Lurking in the shadows of their crushing gravity might be something far stranger. Wormholes disguised as black holes, their true nature hidden behind nearly identical veils of darkness. The idea isn't as far-fetched as it sounds. To an outside observer, both would appear as regions of space where light vanishes, time distorts, and matter spirals inward, never to return. But dig deeper and subtle clues might reveal whether we're staring into a one-way gravitational prison or the mouth of a bridge to another world. The telltale differences lie in the details. While black holes trap everything past their event horizons, a wormhole's throat might not be a true point of no return. Matter entering one could theoretically emerge elsewhere, leaving faint fingerprints in the process. One clue could come from accretion disks, the superheated rings of gas and dust orbiting these objects. Around a black hole, these disks blaze with predictable intensity as material heats up before plunging inward. But a wormhole might siphon some of that matter through its tunnel, causing unexpected flickers or energy drops in the disk's glow. Imagine pouring water down two drains, one leading to a sealed pipe, the other to an open channel. The flow patterns wouldn't match, and neither would the light shows from these cosmic whirlpools. Even more revealing could be what comes out the other side. If a wormhole's distant end dumps energy into another region of space, telescopic surveys might spot unexplained bursts of radiation with no visible source. Picture a hospital detecting X-rays from an empty room, only on a cosmic scale, with gamma-ray flares appearing millions of light-years from any known celestial object. Some astronomers speculate that certain ultra-high-energy cosmic rays, which arrive from seemingly empty voids, could be the exhaust of faraway wormholes, spewing particles that tunneled through spacetime. Then there's the gravitational shadow. The Event Horizon Telescope's landmark image of the black hole in galaxy M87 revealed a dark silhouette ringed by fiery light, a perfect match for predictions. But wormholes might cast distorted shadows, their warped throats bending light in ways that create subtle asymmetries or multiple rings. Recent simulations suggest a wormhole's shadow could resemble a black hole's, but with a faint, ghostly second halo caused by light looping through the tunnel and back out. It's like comparing a coin's shadow to a donut's. The difference is subtle, but in the razor-sharp gaze of next-generation telescopes, it might be detectable. The boldest test: time. Black holes slow clocks to a crawl near their event horizons, but wormholes might twist time in stranger ways. If one end of a wormhole accelerates to near light speed while the other remains stationary, it could create a time difference between its mouths, like two doors to the same room, one leading to Tuesday, the other to Thursday. Matter passing through could emerge before it entered, creating causality defying signatures in the surrounding space. While no such observations exist yet, anomalies in the timing of pulsars or quasars near suspected black holes might one day hint at these temporal quirks. Of course, proving any of this is a monumental challenge. Wormholes masquerading as black holes would be master illusionists, their differences buried in noise and cosmic distance. But the hunt is already underway. Telescopes scanning for gravitational waves are fine-tuning their ability to detect the unique spacetime ripples a wormhole might produce when disturbed, perhaps by a star passing through its throat. Others are developing algorithms to scour galaxy catalogs for the odd gravitational lensing patterns a wormhole's unique mass distribution could create. What makes this theory so electrifying is its audacity. It forces us to question not just what we see, but what we assume. The universe has a habit of hiding its greatest wonders in plain sight, cloaked in the familiar. If even a handful of black holes turn out to be wormholes, it would mean the cosmos has been quietly offering us gateways all along. We just needed to learn how to look. The next time you gaze at an image of a black hole's abyss, remember, it might not be an end at all, but a door waiting to be opened. The early universe was a seething cauldron of energy, where the laws of physics bent under conditions we can barely recreate in our most powerful particle colliders. In that primordial chaos, mere fractions of a second after the Big Bang, spacetime itself might have been stretched and knotted like taffy, forming wormholes as naturally as bubbles in a boiling pot. These ancient structures, forged when the cosmos was hotter and denser than the core of a supernova, could still lurk among us today, hidden relics of the universe's explosive infancy. What makes primordial wormholes so compelling is their potential longevity. Unlike the fleeting wormholes theorized to form in black hole collisions or quantum foam, these early universe tunnels could have been frozen into place as the cosmos expanded. Picture a spiderweb caught in amber, except here, the web is space-time, and the amber is the rapid cooling of the universe during its first moments. As inflation stretched the fabric of reality, these wormholes might have been stretched too, their throats pinned open by the very forces that birthed them. Some models suggest they could span distances far beyond anything we'd expect from naturally forming wormholes today, bridges not just between stars, but between superclusters of galaxies. The key to their survival lies in the exotic conditions of the early universe. Back then, energies were so extreme that matter and gravity behaved differently. Quantum fields that now play by strict rules might have flickered wildly, creating temporary pockets of negative energy, exactly the ingredient needed to prop a wormhole open. As the universe cooled, these pockets could have been locked into the wormhole's structure like cosmic reinforcement rods. It's like building a tunnel through soft clay, then firing it in a kiln until it hardens into ceramic. The result, a wormhole that's not just stable but virtually indestructible across billions of years. Finding these relics wouldn't be easy. They'd likely be camouflaged by cosmic expansion, their endpoints drifting apart over eons. Some might now connect regions so distant that light hasn't had time to traverse the gap since the Big Bang. Others could be dormant, their throats pinched shut until disturbed by a passing star or a surge of dark matter. But clues might lie in the cosmic microwave background, the afterglow of the universe's birth. Tiny anomalies in this radiation, like unexpected temperature fluctuations or odd polarization patterns, could hint at the gravitational shadows of wormholes woven into spacetime's fabric. The most tantalizing possibility, primordial wormholes might not just be artifacts, they could be the universe's original transit system. If advanced civilizations exist, they might have already mapped these ancient shortcuts, turning cosmic archaeology into a roadmap for interstellar travel. After all, why build a wormhole when the universe left perfectly good ones lying around? Whether we ever find them or not, their theoretical existence reminds us that the cosmos doesn't just hide its secrets in the present. It buried some of its greatest treasures in the first moments of time itself. Building a wormhole from scratch would be humanity's ultimate engineering feat, a project that makes putting a man on the moon look like stacking blocks. The sheer audacity of the idea alone is staggering, bending spacetime itself to our will, not by finding a naturally occurring gateway, but by forging one through raw ingenuity. While nature might have left us a few cosmic breadcrumbs, artificial wormhole creation flips the script entirely. It's not about discovery, it's about invention. The roadmap begins where all modern physics breakthroughs seem to start, particle accelerators. Imagine slamming particles together at energies so extreme, they don't just shatter atoms, they momentarily puncture spacetime. Some models suggest that within the fleeting chaos of a high-energy collision, microscopic wormholes could flicker into existence, bridging points separated by less than a proton's width. The Large Hadron Collider already produces temperatures not seen since the universe's first microseconds. Might it, or a successor 1,000 times more powerful, briefly warp spacetime into a stitch-like tunnel? The math tantalizingly allows it, but capturing and stabilizing such an ephemeral wormhole would require precision beyond anything we possess. It'd be like trying to lasso a lightning bolt with thread. Energy manipulation is the next frontier. To prop open a wormhole's throat, we'd need to generate and control negative energy, something no current technology can achieve. Theoretical designs propose using layered quantum fields or Casimir cavities to carve out pockets of this exotic substance, essentially weaving a patch of spacetime that repels rather than attracts. Picture building a bridge where every brick actively resists gravity, creating a self-supporting arch through sheer defiance of physics as we know it. The energy requirements astronomical, stabilizing a wormhole wide enough for a single atom might demand more power than humanity currently generates in a year. Then there's the space-time geometry problem. Crafting a traversable wormhole isn't just about punching a hole, it's about sculpting the surrounding space-time like cosmic clay. Proposals involve precisely arranged rings of ultra-dense matter or spinning superconductors to create the necessary gravitational torsion, twisting space-time until it folds. Some blueprints even call for topological engineering, where quantum fields are tuned to guide space-time into forming a stable throat. It's the difference between digging a random tunnel and constructing a reinforced subway line. One collapses under its own weight, the other holds firm for centuries. The technological hurdles are as numerous as they are daunting. For starters, we'd need materials that don't exist, substances capable of withstanding gravitational tidal forces that would shred neutron stars. Then there's navigation. Even if you built a wormhole, how would you ensure it leads somewhere useful? An uncontrolled exit, it might dump travelers into a star's core or the vacuum between galaxies. Stabilizing both ends simultaneously would require coordination across light years, a feat of timing and communication that laughs at our current understanding of causality. Yet the most sobering challenge might be unintended consequences. Artificial wormholes could catastrophically destabilize if mishandled, potentially collapsing into black holes or unleashing vacuum decay, a theoretical scenario where a bubble of destructive energy expands at light speed, rewriting the fundamental laws of physics in its wake. It's the ultimate measure twice, cut once scenario, except the scissors are made of space-time, and a misstep could unravel reality itself. What keeps scientists pushing forward is the tantalizing principle underlying all these challenges. None of them violate known physics. The universe's rulebook permits wormhole engineering. It just demands near godlike mastery to pull it off. For now, the dream remains locked in equations and thought experiments. But the very fact that we can sketch blueprints for bending the cosmos to our will is a testament to how far we've come and how much further we might yet go. Stepping through a wormhole might be the ultimate cosmic gamble, because what if the tunnel slams shut behind you? The terrifying reality is that even the most meticulously engineered wormhole could collapse catastrophically mid-transit, turning a shortcut across the stars into a one-way trip to oblivion. Unlike bridges made of steel and concrete, these space-time tunnels aren't held up by girders and bolts. They're propped open by the universe's most fragile balancing act, and the slightest disruption could send the whole structure crashing down. Imagine you're halfway through a wormhole when instability takes hold. The exotic matter lining the throat, the very scaffolding keeping the passage open, could fluctuate or fail. In an instant, the walls of the tunnel might begin contracting like a noose, pinching the wormhole shut with forces rivaling a supernova. Anything inside when this happens wouldn't just be crushed. The extreme gravitational tides would stretch matter into spaghetti like strands before vaporizing it completely. Compounding the horror is the timescale. From a traveler's perspective, this collapse could unfold in milliseconds, leaving no chance to react or escape. The dangers don't stop at sudden implosions. Even a partial collapse could strand travelers in a nightmarish limbo. Picture the wormhole's throat narrowing like a clogged pipe, severing the connection between its ends. You'd emerge, if you emerge at all, in an isolated pocket of distorted spacetime, cut off from both your origin and destination. Some models suggest such a failure could twist the wormhole's remnants into a closed time-like curve, trapping you in a loop where cause and effect unravel. One moment you're cruising through the tunnel, the next you're reliving the same catastrophic second over and over, like a record skipping on the grooves of reality itself. Then there's the domino effect. A collapsing wormhole wouldn't just vanish quietly, it could unleash violent spacetime shockwaves. The sudden release of pent-up gravitational energy might ripple outward as gamma-ray bursts or gravitational waves intense enough to sterilize nearby star systems. Historical supernova records show unexplained energy spikes that some theorists now speculate could have been the death throes of natural wormholes. If artificial ones fail just as spectacularly, their construction would demand fail-safes beyond anything we've engineered. Perhaps quantum stabilization fields or emergency anchor systems to bleed off energy gradually. Perhaps the most unsettling risk is quantum unpredictability. On microscopic scales, wormholes might flicker in and out of existence due to vacuum fluctuations. Scale that up to a traversable wormhole, and you've got a structure that could vanish without warning, like a soap bubble popping midair. Some equations even hint that conscious observation could influence stability, a twisted variation on the quantum measurement problem where simply perceiving the wormhole might nudge it toward collapse. It's as if the universe itself resists these shortcuts, erasing them the moment we try to take control. Surviving transit would require more than sturdy hull plating. Ships might need exotic matter shielding to reinforce the wormhole's walls locally, like portable atmospheric bubbles for deep-sea divers. Navigation systems would have to monitor throat stability in real time, plotting escape trajectories the instant fluctuations are detected. And even then, the margins for error would be vanishingly thin. The cruel irony, the same exotic physics enabling wormholes also makes their failures uniquely horrifying, not just dead ends, but reality-warping traps where the rules of existence itself start to fray. Yet for all these nightmares, the allure remains, because if humanity ever learns to tame these risks, the payoff isn't just new worlds, it's rewriting what's possible in the cosmos. Every great frontier has demanded those willing to face its dangers, from sailors braving uncharted oceans to astronauts vaulting beyond Earth's grip. The difference here is that wormholes don't just test our courage, they test our very understanding of the universe's foundations. And sometimes the only way to discover where those foundations bend is to step into the unknown, eyes wide open to the abyss. What if every wormhole isn't just a cosmic shortcut but a doorway to another universe entirely? The multiverse hypothesis, once relegated to the fringes of theoretical physics, now suggests our universe might be one bubble in an infinite foam of realities, each with its own laws, histories, and perhaps even versions of us. And wormholes could be the threads stitching these parallel worlds together, hidden tunnels in the fabric of existence leading not just across space, but between entirely different dimensions. This audacious idea emerges from the strange marriage of quantum mechanics and cosmology. Quantum theory tells us that particles can exist in multiple states simultaneously until observed, a principle called superposition. Extend this to the cosmic scale, and you get the many worlds interpretation, where every quantum decision spawns a new universe. Now imagine a wormhole forming at the moment of cosmic inflation, when space-time was stretching faster than light. As the universe branched into countless variations, these tunnels might have become entangled across realities, like roots connecting separate trees in a vast forest. The math behind this is as elegant as it is mind-bending. Certain solutions to Einstein's equations allow for wormholes to link not just different points in spacetime, but different spacetimes altogether. Picture two soap bubbles floating close together. Normally, their surfaces never touch, but if you puncture one with a needle, you create a bridge between them. In cosmological terms, a wormhole could be that needle, threading through the higher dimensional bulk that separates parallel universes in models like string theory's brain cosmology. Evidence for this might already be hiding in plain sight. Some physicists speculate that dark energy, the mysterious force accelerating the universe's expansion, could be the gravitational pull of neighboring universes leaking through these wormholes. Others point to anomalies in the cosmic microwave background, like the infamous cold spot, as potential bruises where our universe once brushed against another. Even quantum entanglement, with its spooky instantaneous connections across distances, might find explanation in micro-wormholes tethering particles across parallel realities. But traversing such a wormhole would be unlike anything we've imagined. The throat might not just bend space, it could twist the very laws of physics. Step through, and you might emerge in a universe where gravity is repulsive, time flows backward, or matter never formed. Some models suggest the act of crossing could destabilize the wormhole, sealing you forever in a reality where the constants of nature render life impossible. It's the ultimate cosmic dice roll. One wrong step, and you're not just lost in space, you're erased from the foundational rules of existence itself. Yet the most profound implication isn't about travel, it's about communication. If multiverse wormholes exist, even at microscopic scales, they could allow information transfer between universes. Quantum signals tunneling through might explain mysterious observations, like particles appearing to remember states they never experienced in our timeline. Advanced civilizations could theoretically exploit these links, sending encoded data across realities like cosmic radio transmissions. We might even be surrounded by faint echoes of other universes, whispering through wormholes too small to see. Of course, skeptics highlight the gaps. No direct evidence proves other universes exist, let alone that wormholes connect them. The energy required to stabilize an inter-universe tunnel might dwarf anything the observable universe contains. And if wormholes do bridge realities, why haven't we detected anomalous matter or energy bleeding through? Perhaps because the walls between universes are thicker than we think, or because whatever lies on the other side is too alien to recognize. What makes this theory so captivating is how it transforms wormholes from mere transportation devices into cosmic Rosetta Stones. Each one could be a dictionary translating between different versions of reality, a living experiment in how physics might vary across the multiverse. Whether they are proven or not, multiverse wormholes challenge us to think bigger than what's out there and start asking what else is out there. The answer might rewrite not just our place in space, but our understanding of existence itself. Dark energy and wormholes might seem like unrelated cosmic phenomena, one relentlessly pushing the universe apart, the other potentially bending it into shortcuts, but dig deeper and their connection becomes eerily plausible. Picture a balloon inflating, its surface stretching thinner with every breath. Now imagine tiny pinpricks dotting that balloon, wormholes struggling to maintain their shape as the fabric of spacetime itself expands at an accelerating rate. That's the universe we live in, where dark energy's mysterious influence could be quietly dictating the fate of every hypothetical wormhole threading through the cosmos. The numbers are staggering. Dark energy accounts for nearly 70% of the universe's mass energy content, driving galaxies apart faster and faster. If wormholes exist, they're not immune to this cosmic tug-of-war. Theoretical models suggest that as space-time stretches, a wormhole's throat could be pulled taut like taffy, forcing it either to snap shut or expand uncontrollably. The deciding factor, the balance between dark energy's outward push and the wormhole's internal scaffolding, exotic matter or other stabilizing mechanisms fighting to keep the passage intact. It's a silent battle happening on scales we can barely comprehend, where the fate of interstellar travel might hinge on a force we can't even directly observe. Stranger still, dark energy might not just disrupt wormholes, it could create them. Quantum field theory suggests that the vacuum of space isn't truly empty. It's a frothing sea of virtual particles and energy fluctuations. Some physicists speculate that dark energy's repulsive effect could amplify these quantum tremors, twisting space-time into microscopic wormholes that blink in and out of existence. These wouldn't be the grand interstellar tunnels of science fiction, but their existence would imply that dark energy isn't just tearing the cosmos apart, it's also stitching it together in ways we're only beginning to glimpse. The most tantalizing possibility, wormholes might be leaking dark energy. If a wormhole's throat connects vastly distant regions of space, the difference in dark energy density between its ends could create a pressure gradient, a cosmic siphon funneling energy from one side to the other. Telescopes have spotted unexplained voids where dark energy seems unusually concentrated, and while conventional explanations exist, the fringe hypothesis remains. Could these be the exhaust ports of ancient wormholes, venting dark energy like steam from a kettle? Yet for all these speculative connections, the irony cuts deep. Dark energy's expansion may ultimately render wormhole travel impossible over cosmic timescales. As the universe grows emptier and more diffuse, the energy required to stabilize a traversable wormhole could outpace what any civilization could harness. The universe's accelerating expansion might be writing an expiration date on interstellar shortcuts, burying them behind horizons of distance we'll never cross. Unless, of course, we learn to hitch a ride on dark energy itself, using the universe's own expansion as the engine for our journeys. Now that's a twist even Einstein might not have seen coming. Neutron stars are the universe's ultimate pressure cookers, cosmic remnants so dense, a teaspoon of their material would weigh 1 billion tons on Earth. But what if these extreme objects aren't just dead stars? What if their crushing gravity does something even stranger, warping spacetime so severely that it folds into a wormhole? The idea isn't as outlandish as it sounds. When matter collapses under such unimaginable pressure, the rules of physics as we know them begin to warp. At these densities, Einstein's equations suggest spacetime itself could twist into knots, forming tunnels hidden deep within the star's core, structures so stable they might outlast the neutron star itself. The clues lie in the bizarre physics at play. Neutron stars are born from supernovae so violent they compress protons and electrons into a sea of neutrons, creating a material denser than anything else in the observable universe. But dig deeper and quantum effects start to rebel. Some theories propose that at these extremes, the neutrons might transform into exotic quark matter, a state where the fundamental building blocks of matter break free from their usual rules. If this quark gluon plasma forms in just the right configuration, it could generate the negative energy densities needed to prop open a microscopic wormhole. Picture a tiny, self-sustaining tunnel threaded through the star's heart, hidden beneath miles of ultra-dense crust. Spotting these hidden wormholes wouldn't be easy, but neutron stars offer a few tantalizing hints. Take pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Normally, their pulses are metronome regular, but some exhibit sudden, unexplained glitches where their rotation speeds up or slows down abruptly. While conventional explanations involve starquakes or internal fluid dynamics, a handful of theorists suggest these anomalies could be signs of something more exotic. A wormhole throat flexing inside the star, momentarily altering its moment of inertia. Imagine a gyroscope with a hidden cavity. When the cavity shifts, so does the spin. If a wormhole inside a neutron star wobbled or expanded slightly, it might leave fingerprints in the star's rotation. Even stranger are the thermal signatures. Neutron stars should cool predictably over time as their insane heat radiates away. Yet some defy expectations, staying mysteriously warm for millennia. One provocative explanation: a wormhole inside could be acting as a conduit for energy, siphoning heat from an unseen companion, another neutron star, a black hole, or even an entirely different region of spacetime. It's like finding a pipe hidden in a glacier, secretly feeding it warm water from miles away. Advanced X-ray telescopes hunting for unexplained hotspots or asymmetric radiation patterns around neutron stars might one day catch these subtle leaks. Then there's the gravitational wave connection. When neutron stars collide, as witnessed in 2017, they send ripples through spacetime detectable by observatories like LIGO. These waves carry detailed information about the star's internal structure. Most models assume neutron stars are uniform, but if one harbored a wormhole, the resulting gravitational wave signal would bear unique distortions. Picture throwing two stones into a pond, one solid, one hollow. The ripples they create wouldn't match. Future detectors with even greater sensitivity might pick up these anomalies, revealing hidden structures lurking inside. The boldest implication: if neutron stars naturally form wormholes, they could be strewn across the galaxy like hidden subway stations waiting for someone to find the map. Civilizations advanced enough to identify and stabilize these tunnels wouldn't need to build their own. They just need to unlock what the universe has already provided. Of course, mining a wormhole from a neutron star's core would be like trying to extract a diamond from the center of a volcano. The gravitational tides alone would shred any known material, and the radiation environment is beyond lethal. But for a species with the right technology, these cosmic vaults might hold the ultimate treasure, a pre-built highway through spacetime. Until then, the search continues. Every odd pulsar glitch, every inexplicably warm neutron star, every anomalous gravitational wave could be a breadcrumb leading to one of the universe's best-kept secrets. Whether or not these ultra-dense giants hide wormholes in their cores, the mere possibility forces us to rethink how matter behaves under extremes we can barely fathom. And in that rethinking, we might just find the keys to the cosmos. Time doesn't flow evenly across the universe. It bends, stretches, and warps under gravity's influence. And if you're standing near a wormhole's entrance, that distortion could twist time itself into unrecognizable shapes. Unlike the predictable tick of a clock on Earth, a wormhole's gravitational grip might make minutes stretch into years or compress centuries into seconds. This isn't science fiction. It's the brutal reality of Einstein's relativity, where time becomes as malleable as clay in the hands of spacetime's most extreme architectures. The eerie parallels to black holes are uncanny. Near a black hole's event horizon, time slows to a crawl for an outside observer. Drop a clock toward one, and it would appear to tick slower and slower until freezing entirely at the point of no return. But wormholes add a sinister twist. They could create asymmetric time dilation. Picture one end of a wormhole anchored near Earth while the other rockets away at near light speed. Due to relativistic effects, time would pass far slower for the moving end. Return it to Earth after a decade, and you'd have a bridge connecting two moments in time stepped through, and you might emerge before you even left. Here's where things get unsettling. Unlike black holes, which simply slow time near their singularities, wormholes could tangle causality itself. If you take a leisurely stroll through a time-dilated wormhole, you might exit to find your home planet centuries older, or worse, arrive before your own birth. The equations permit scenarios where messages could be sent backward in time, creating paradoxes that make the classic grandfather paradox look tame. Imagine a civilization that builds a wormhole time machine only to receive blueprints for the device from its own future. The very act of creation could loop endlessly with no clear origin point. Yet there's a crucial distinction between black hole and wormhole time dilation. A black hole's time warp is a one-way street. Once you're close enough to experience extreme dilation, you're probably not coming back. Wormholes, at least in theory, offer a round-trip ticket, but the price might be your place in history. Calculations show that even a stable wormhole's time differential would expose travelers to tidal forces capable of shredding matter unless meticulously controlled. It's like threading a needle while riding a roller coaster, possible in theory, but requiring precision beyond anything we can currently fathom. The most haunting implication: natural wormholes might already be distorting time across the cosmos. If one formed near a neutron star or in the turbulent wake of a galactic collision, its time-warping effects could be imprinted on the light passing through it. Astronomers hunting for anomalous gamma-ray bursts or inexplicably redshifted quasars might already be staring at the fingerprints of wormhole time dilation without realizing it. The universe could be littered with hidden clocks ticking at different speeds, each one a gateway not just to another place but to another when. Whether we'll ever harness this phenomenon remains an open question. The energy required to stabilize a time-shifting wormhole might dwarf the output of entire galaxies, and the risks temporal paradoxes, causality violations, or even the collapse of the wormhole mid-journey make the endeavor more perilous than any voyage humanity has ever attempted. But the mere possibility reshapes how we see time itself, not as an immutable river, but as a labyrinth where the right doorway could lead anywhere or anyone. Quantum gravity is the holy grail of modern physics, a theory that could finally reconcile the cosmic and the microscopic, merging Einstein's general relativity with the bizarre rules of quantum mechanics. And if such a theory exists, it might hold the key to understanding wormholes not as mathematical oddities but as fundamental features of the universe's architecture. Right now, these two pillars of physics speak different languages. General relativity paints gravity as the curvature of spacetime, while quantum mechanics describes particles dancing in probabilistic clouds. Wormholes caught between these worlds demand a fluent translator, a framework where spacetime's elasticity meets quantum unpredictability in perfect harmony. Enter loop quantum gravity, one of the leading candidates for this grand unification. Unlike string theory's extra dimensions, this approach imagines spacetime as a network of tiny, indivisible loops, a fabric woven from finite threads rather than an infinitely divisible continuum. In this view, wormholes could emerge naturally as knots in spacetime's weave, where loops twist back on themselves to form shortcuts. Picture a knitted sweater. Pull two distant stitches together, and the yarn connecting them forms a hidden tunnel through the fabric. The implications are staggering. If spacetime is inherently granular at the smallest scales, wormholes might not require exotic matter or cosmic engineering. They could be unavoidable byproducts of quantum geometry woven into reality's very blueprint. String theory offers another tantalizing path. Here, wormholes might arise from the interactions of cosmic strings, one-dimensional energy filaments vibrating in higher dimensions. Certain string theory models suggest that when these strings collide or tangle, they could pinch spacetime into wormholes, much like how twisting a rubber band creates loops. The elegance of this idea lies in its economy. The same fundamental objects that give rise to particles and forces might also spawn spacetime's hidden passageways. Even more compelling, string theory's holographic principle, where our three-dimensional universe is a projection from a two-dimensional boundary, hints that wormholes could be encoded in quantum entanglement patterns on that lower dimensional surface. It's as if the universe stores its shortcuts in a cosmic QR code we're just learning to scan. Recent breakthroughs are bringing these theories from abstraction toward testability. In 2021, physicists using quantum computers simulated simplified models of spacetime, observing wormhole-like information transfer between entangled particles. The experiment didn't create an actual wormhole, but it showcased how quantum systems might mimic spacetime's behavior, a crucial step toward proving they're two sides of the same coin. Meanwhile, gravitational wave observatories are hunting for anomalies in black hole mergers that could betray quantum gravity effects, perhaps even evidence of microscopic wormholes flickering into existence during these violent events. Yet the challenges remain immense. Quantum gravity operates at the Planck scale, distances so tiny they make atoms look like planets. Probing this realm directly would require particle accelerators the size of galaxies. Some theorists propose workarounds, like searching for quantum gravity's fingerprints in the cosmic microwave background or the spin orientations of distant pulsars. Others hope that wormholes themselves, if detected, could serve as nature's own particle colliders, their extreme environments amplifying quantum gravity effects to observable levels. Perhaps the most profound insight quantum gravity offers is that wormholes might not be bridges through space-time, they could be stitches in its very fabric. In this light, the quest to understand them isn't just about unlocking interstellar travel, it's about deciphering the universe's deepest code, Every equation, every simulation, every flicker of data brings us closer to a revelation that the cosmos might be far more interconnected and far stranger than we ever imagined. Hollywood has a love affair with wormholes, those shimmering gateways that let heroes zip across galaxies between lunch breaks. But how much of what you see on screen holds up to real physics? Surprisingly, some blockbusters nail key concepts, while others take creative liberties that would make Einstein raise an eyebrow. Let's start with the good. Christopher Nolan's Interstellar famously consulted physicist Kip Thorne to depict Gargantua, the film's supermassive black hole with a wormhole companion. The result, a stunningly accurate visualization of gravitational lensing, where light bends around the wormhole's mouth, warping background stars into a halo of stretched starlight. Even the wormhole's spherical shape aligns with theory, a three-dimensional shortcut through higher dimensions, not some flat magical portal. Where fiction often stumbles is stability. Movies like Stargate show characters strolling through wormholes like subway tunnels, ignoring the cosmic hazards real science predicts. In reality, traversing a wormhole without exotic matter scaffolding would be like tightrope walking over a volcano. The moment you stepped in, tidal forces would stretch you into a human noodle before quantum fluctuations shredded your atoms. Then there's Event Horizon, which imagines a wormhole to hell, a thrilling premise, but one that conflates wormholes with black hole singularities. Real wormholes don't lead to nightmare dimensions. They'd either transport you somewhere calculable or collapse in a blaze of gamma rays. Time dilation gets butchered too. Thor treats the Bifrost as a wormhole-esque bridge where time passes equally on both ends, a cozy idea, but dead wrong. Real wormholes near massive objects would warp time dramatically. Arrive at your destination and everyone you know might have aged decades. Contact, based on Carl Sagan's novel, strikes a better balance. Its wormhole journey includes eerie time distortions and a gut-wrenching corridor of chaos, closer to the disorienting space-time turbulence physicists expect. The biggest exaggeration, instantaneous travel, from Star Trek's transwarp conduits to Avengers. In games' quantum realm jumps, films rarely acknowledge the energy cost. Stabilizing a wormhole large enough for a ship might require compressing Jupiter into exotic matter, something Tony Stark's arc reactor definitely couldn't power. But where sci-fi deserves credit is inspiration. By bending the rules, storytellers spark public fascination that fuels real research. After all, today's far-fetched fantasy could be tomorrow's Nobel Prize breakthrough, as long as we remember that wormholes aren't magic. They're physics at its most extreme, where the line between science and fiction isn't broken, just bent. Imagine sending a message across the galaxy and receiving a reply before you've even finished your coffee. Wormhole communication turns this sci-fi dream into a tantalizing theoretical possibility, one where the limitations of light speed delays vanish and interstellar conversations happen in real time. Unlike radio signals that take years to crawl between stars, a message transmitted through a wormhole's throat could bridge thousands of light years instantaneously, bending not just space but the very concept of cosmic distance. The implications are staggering. Colonies on Proxima Centauri could video call Earth with no lag, or scientists on opposite sides of the Milky Way could collaborate as seamlessly as neighbors. But the path to making this work is riddled with hurdles that defy both physics and imagination. First, there's the problem of bandwidth. Even if a wormhole could be stabilized for communication, its throat might only accommodate a trickle of information. Quantum fluctuations near the wormhole's walls could scramble signals like static on a radio, reducing complex messages to gibberish. Some models suggest encoding data in entangled particles, quantum bits that maintain coherence through the tunnel. But maintaining entanglement across such extreme space-time curvature is like trying to play a violin in a hurricane. The slightest disruption could sever the connection, leaving messages fragmented or lost. Then there's the energy cost. Keeping a wormhole open long enough to transmit meaningful data might demand power outputs rivaling a small star. Laser pulses or modulated neutrino beams could serve as carriers, but amplifying these signals to traverse the wormhole's gravitational tides without distortion would require technologies we've barely conceptualized. It's the difference between shouting across a canyon and building a fiber optic cable. Through it, one's simple but unreliable, the other precise but astronomically complex. Security is another nightmare. A wormhole communication network would be the ultimate high-value target, vulnerable to hijacking or sabotage. Unauthorized access could allow eavesdropping on interstellar transmissions or even the injection of malicious data. Imagine a virus designed to destabilize the wormhole itself. Encryption would need to evolve beyond quantum-proof algorithms to something like spacetime-proof cryptography, where the very geometry of the wormhole's throat acts as a firewall. Perhaps the most mind-bending implication is temporal desynchronization. If one end of a wormhole moves at relativistic speeds relative to the other, time dilation could twist communication into a paradox. Send a message through a high-speed wormhole, and the reply might arrive before you sent the original signal. Civilizations would need to establish protocols to handle causality violations like cosmic timestamps to prevent recursive loops where messages spawn infinite copies of themselves. Yet for all these challenges, the payoff would redefine civilization. Archaeologists could study alien ruins in real time alongside distant colleagues. Artists could share works across star systems without waiting centuries for acknowledgement. And humanity, fractured across the stars, might finally feel connected in ways light-speed lag never allowed. Wormhole communication isn't just about breaking distance, it's about stitching the cosmos into a single, living network where no world is ever truly alone. One thing's certain, if this future arrives, the first message sent won't be a dry scientific report. It'll be something simpler, bolder, a declaration that across the unimaginable void we found a way to whisper, "Can you hear me now?" And mean it. Stepping through a wormhole might rewrite the rules of space travel, but it could also rewrite your DNA. The human body, evolved for Earth's gentle environment, would face a gauntlet of hazards in a cosmic short-cut, forces so extreme they'd make the vacuum of space feel like a vacation. Radiation alone poses a nightmare scenario. Wormholes, especially those anchored near high-energy regions like quasars or neutron stars, could flood their throats with gamma rays and cosmic particles moving at near-light speeds. Without shielding equivalent to a small moon's worth of lead, traversing one would be like swimming through a particle accelerator. Even brief exposure could scramble cells beyond repair, triggering radiation sickness in minutes and cancer, risks that dwarf Hiroshima's aftermath. And that's just the start. Tidal forces present another gruesome challenge. A wormhole's throat isn't a tidy tunnel, it's a maelstrom of gravitational gradients. Picture the difference between Earth's gravity at sea level versus mountaintops, magnified by a factor of billions. Near the wormhole's narrowest point, these forces could stretch and compress your body simultaneously, pulling your head toward Proxima Centauri while your feet linger near Earth. The effect: spaghettification, the same grisly fate awaiting black hole adventurers. Calculations suggest even a stable wormhole would generate tides strong enough to rupture organs unless its throat was engineered to planetary scales, a corridor thousands of miles wide to distribute the strain. Forget cramped spaceships, you'd need a floating city just to survive transit. Then there's the temporal whiplash. If the wormhole's ends experience different time dilation, say, one near a black hole, the other in deep space, your cells might age unevenly mid-journey. Enzymes critical for metabolism could decelerate in your liver while racing ahead in your brain, triggering cascading biological failures. Early experiments with atomic clocks on the ISS show how mere microseconds of divergence affect human physiology. Wormhole time skews could be exponentially worse. Astronauts might emerge with the muscle atrophy of a decade-long mission despite a subjective trip lasting minutes. The psychological toll could be equally brutal. Wormhole travel wouldn't just bend space, it might shatter perception. Simulations of warped spacetime predict visual distortions akin to funhouse mirrors magnified to cosmic scales. Stars ahead could appear as fractured smears. The wormhole's walls might ripple with impossible geometries that trigger seizures or existential panic. Add in potential temporal disorientation, memories arriving out of sequence, déjà vu loops, and even the sturdiest minds could unravel. Yet the most insidious threat might be quantum. At Planck-scale distances, spacetime's foam-like structure could interact unpredictably with organic matter. Some theories suggest traversing a wormhole might entangle your atoms with its walls, literally knitting your biology into the fabric of the tunnel. Emerge intact, and you could carry fragments of the wormhole's quantum state within you, a walking anomaly with unknown long-term effects. Surviving these horrors would demand more than advanced tech. It would require reimagining humanity itself. Genetic modifications to bolster radiation resistance, cybernetic implants to regulate tidal stresses, even artificial consciousness buffers to withstand perceptual chaos. Alternatively, we might abandon biological travel entirely, sending quantum-scanned consciousness or self-replicating probes instead. Whatever the solution, one truth becomes clear: wormholes aren't just shortcuts through space. They're filters testing whether we're truly ready to step beyond the cradle of Earth's biosphere, or if the cosmos reserves its highways for those willing to become something else. The Big Bang wasn't just the universe's birth, it might have been the ultimate wormhole factory. In those first searing moments, when reality was hotter than a trillion suns and denser than a neutron star, spacetime itself could have been stretched and knotted into countless tiny tunnels. These primordial wormholes wouldn't be like the cosmic shortcuts we imagine today. They'd be cosmic fossils, frozen into the fabric of the universe as it expanded, relics of a time when the laws of physics as we know them hadn't yet settled into place. If they survived, they could be whispering secrets about the universe's first moments, clues buried in the very architecture of spacetime. Picture the early universe like a pot of water at a rolling boil. Bubbles form and pop constantly, each one a fleeting distortion in the liquid. Now replace those bubbles with wormholes, tiny spacetime loops forming and collapsing in the quantum chaos. But as the universe expanded and cooled, some of these structures might have been locked in by the rapid stretching of cosmic inflation, like insects preserved in amber. These wouldn't be the carefully balanced wormholes of later theories. They'd be wild, twisted things shaped by energies we can barely fathom. Some could have stretched across the newborn cosmos, linking regions that inflation later tore apart, meaning a wormhole's two ends might now sit billions of light-years apart, threading through the universe like a sewing needle through an ever-expanding cloth. The real treasure lies in what these ancient tunnels could tell us. Wormholes forged in the Big Bang's crucible would carry imprints of conditions we can never recreate, temperatures so high they unified all fundamental forces, densities where quantum gravity ruled supreme. If we could study one up close, it might reveal how spacetime itself behaves under such extremes, offering clues about phenomena like quantum foam or the true nature of dark energy. Some models even suggest these wormholes could contain trapped echoes of the universe's first particles, like cosmic time capsules holding samples of reality's original ingredients. Imagine cracking open a wormhole and finding primordial quarks or relics of supersymmetry inside, perfectly preserved from 13.8 billion years ago. But how would we ever find them? Primordial wormholes, if they exist, would be masters of disguise. Many could be microscopic, hiding in plain sight as quantum fluctuations in empty space. Others might have grown with cosmic expansion, their mouths now disguised as gravitational anomalies, perhaps masquerading as rogue black holes or unexplained dark matter clumps. The key to spotting them could lie in their gravitational fingerprints. Unlike black holes which warp light predictably, a primordial wormhole's twisted geometry might bend light in odd ways, creating double images of distant stars or anomalous distortions in the cosmic microwave background. Some astronomers are already scouring sky surveys for these subtle aberrations, like detectives searching for scratches on a cosmic window that hint at hidden passages beyond. The boldest idea, these wormholes might not just be relics, they could be the universe's original umbilical cords. Inflation theory suggests the Big Bang spawned not just our universe, but perhaps countless others in a vast multiverse. Primordial wormholes could be the frayed ends of those connections, vestigial links to sibling universes now forever out of reach. If so, studying them wouldn't just illuminate our origins, it could prove we're part of something immeasurably larger. Until then, they remain one of cosmology's most tantalizing what-ifs, ghostly threads woven into reality's fabric, waiting to be pulled. Navigating a wormhole would be like threading a needle while blindfolded on a roller coaster, precision and peril in equal measure. Even if we miraculously stabilized one, the journey through its throat presents a gauntlet of hazards that make interstellar travel look like a Sunday drive. At the top of the list, singularities, those gravitational whirlpools lurking in poorly mapped wormholes, ready to shred matter into atomic confetti. Unlike black holes, where singularities sit predictably at the center, wormholes could hide these spacetime ruptures anywhere along their length, like invisible potholes on a cosmic highway. One wrong turn and your ship gets spaghettified before the nav computer can scream a warning. Plotting a safe path demands more than just star charts. Wormhole geometry twists like a Möbius strip, warping the very concept of direction. Light bends so severely that traditional sensors might show false exits or phantom obstacles. Imagine driving through a tunnel where the rearview mirror shows the road ahead bending upward while your windshield displays it curving down. Stabilized wormholes, like those proposed by Morris and Thorne, offer smoother rides, but their throats still churn with quantum turbulence. Microscopic fluctuations in spacetime could amplify mid-transit, shaking a ship like a tin can in a hurricane. Without active stabilization fields adjusting thousands of times per second, even a safe wormhole might ripple apart under the stress of traversal. Solutions hover at the edge of possibility. Quantum-entangled beacons could act as cosmic breadcrumbs, creating a real-time map of the wormhole's internal shifts. Deploy self-replicating probes ahead of the main vessel. Think of them as interstellar canaries in a coal mine to test path stability. Some theorists propose using negative energy buoys to reinforce the throat during transit, like inflating a temporary scaffold as you pass. The real game changer, AI pilots trained on quantum gravity simulations, capable of adjusting course femtosecond before space itself buckles. Yet the cruelest irony might be causality itself. Navigate too well and you risk arriving before you left, a glitch no algorithm can debug. Master the wormhole's twists and you might just untangle time itself. With consequences no roadmap can predict. What if wormholes aren't just cosmic shortcuts, but the universe's ultimate recycling system? Picture a vast, interconnected network of tunnels shuttling matter and energy across space and time, redistributing the building blocks of reality like a celestial conveyor belt. This mind-bending theory suggests that wormholes could be nature's way of balancing the cosmic ledger, ensuring no particle goes to waste in the grand economy of the universe. Consider the fate of a dying star. When a massive star collapses into a black hole, most of its matter vanishes behind the event horizon, seemingly lost forever. But what if some of that material gets funneled through a wormhole, emerging light years away as raw fuel for new star formation? Simulations of rotating black holes show how their intense gravitational fields might twist spacetime into temporary wormhole-like structures, ejecting matter through relativistic jets. These jets, observed blasting from active galactic nuclei, could be the visible exhaust of a hidden recycling process, spewing processed stellar material back into the cosmic ecosystem. The implications for galactic evolution are staggering. Wormholes operating as recycling chutes might explain mysterious phenomena like dark matter distribution. If exotic particles get transported through these tunnels, they could accumulate in patterns that defy conventional gravity models. Even more provocative, the missing baryon problem, where astronomers can't account for about half the normal matter predicted to exist. Could these absent atoms be hiding in transit through a network of wormholes, slowly leaking back into visible space over billions of years? On the grandest scale, this recycling could solve one of cosmology's biggest puzzles: entropy. The universe inevitably marches toward disorder, yet wormholes might provide a loophole. By shuffling energy from overcrowded regions like galaxy clusters to sparse voids, they could act as spacetime's pressure valves, delaying heat death by maintaining equilibrium. It's like a cosmic version of composting, turning the spent remains of dead stars into fertile ground for new creation. The most poetic version of this theory suggests wormholes aren't accidental features, but deliberate infrastructure woven into the universe's fabric. Just as trees exchange nutrients through fungal networks beneath the soil, galaxies might share resources through these hidden conduits, forming a symbiotic web across the cosmos. The universe, in this view, isn't just expanding, it's breathing, circulating its essence through spacetime's secret passages. Of course, proving any of this remains a monumental challenge. Wormhole recycling would leave subtly different fingerprints than conventional astrophysical processes, perhaps slight anomalies in the metallicity of stars at the edges of voids, or unusual correlations between distant quasars. Next-generation telescopes mapping the cosmic web in unprecedented detail might one day spot the telltale signs of matter slipping between the cracks of reality. Whether wormholes truly serve as the universe's recycling system or not, the theory forces us to rethink cosmic ecology. It paints a picture of a universe that's not just expanding chaotically, but perhaps managing its resources with a sophistication we're only beginning to glimpse. Far from being destructive anomalies, wormholes might be the ultimate cosmic custodians, ensuring that every atom, every photon, gets infinite chances to play its part in the story of existence. The universe doesn't always play by Einstein's rules, and neither might wormholes. While general relativity gives us the classic blueprint for these cosmic shortcuts, alternative physics theories paint wilder, weirder possibilities. Take loop quantum gravity, where spacetime isn't smooth and continuous, but a shimmering tapestry of finite, interwoven loops. Here, wormholes aren't anomalies, they're natural knots in the fabric, emerging where these quantum threads tangle and reconnect. Picture a woven sweater snagging on a branch. The resulting loop isn't a flaw, but an inevitable feature of the structure. In this view, traversable wormholes could form spontaneously, woven into reality's very foundation rather than engineered through exotic matter. The catch: their stability depends on the universe's underlying quantum geometry, meaning a wormhole's lifespan might be dictated by the ebb and flow of spacetime's tiniest building blocks. Causal dynamical triangulation takes this further, reimagining spacetime as a mosaic of microscopic, ever-shifting triangles. Wormholes here arise when these geometric tiles fold into higher dimensional shapes, like origami creases piercing through paper. Unlike the smooth tunnels of relativity, these wormholes would be jagged, fractal-like structures, more cosmic honeycombs than symmetrical bridges. The theory's simulations show spacetime organizing itself into tunnels during certain quantum phases, hinting that wormholes might be as fundamental to the universe's architecture as atoms are to matter. What's startling is how these models sidestep the need for exotic matter altogether. Stability comes from the geometry itself, locked in place by quantum rules we're only beginning to decode. Then there's the radical approach of entropic gravity, which suggests gravity isn't a fundamental force but an emergent effect of quantum information scrambling. In this framework, wormholes could be spacetime's way of resetting entropy like cosmic shortcuts for information flow. Imagine a computer overheating from data overload. A wormhole might act as a cooling vent, redistributing entropy across the universe to prevent localized collapses. These tunnels wouldn't just connect places, they'd balance the cosmos's hidden ledger, ensuring no region bears too much informational weight. It's a vision where wormholes are less like subway tunnels and more like the veins of a living organism pulsing with quantum data. Even string theory, with its curled-up extra dimensions, offers wormholes a playground beyond our 3D intuition. Here, traversable tunnels might form when higher-dimensional branes collide or warp, creating bridges inaccessible to low-dimensional travelers like us unless we learn to unravel the hidden dimensions. Think of ants crawling on a newspaper. To them, the page is flat until it's crumpled, revealing folds that bring distant points into contact. String-theoretic wormholes could operate similarly, with their true structure visible only from a higher dimensional vantage point. The beauty of these alternate theories isn't just their imagination, it's how they reframe wormholes from rare marvels to inevitable features. Whether knotted quantum threads, geometric mosaics, or entropy valves, each model suggests the universe might be threaded with shortcuts we've yet to recognize. And that's the ultimate tease. The keys to interstellar travel could be hiding in equations we haven't fully written yet. The countdown to humanity's first wormhole transit begins not with rocket fire, but with a hum, a resonance so deep it vibrates in the bones of every crew member strapped into the Odyssey. This isn't a ship in the traditional sense. It's a quantum-stabilized capsule, its hull woven with metamaterials designed to repel spacetime itself. Inside, 6 astronauts, selected as much for their psychological resilience as their technical skill, monitor holographic displays that flicker with data from the wormhole's throat. Dubbed Einstein-Rosen 1, the structure hovering ahead isn't some cosmic accident. It's the culmination of a century's research, an artificial tunnel painstakingly held open by rings of negative energy plasma, their containment fields singing at the edge of stability. The destination, a carefully chosen point near Proxima Centauri's icy rogue planet, Nemesis 3b. Not for its habitability, its surface is a barren wasteland at -200 degrees, but for its gravitational signature. The planet's steady pull acts as a cosmic anchor, preventing the wormhole's exit from drifting mid-transit. Telescopes had mapped the target for decades, but now, as the Odyssey's AI confirms alignment, the reality hits. This jump isn't just a test. It's a one-way gambit to plant humanity's flag on the other side of interstellar space. Crew dynamics verge on surreal. Commander Elias Vance, a veteran of Mars' first settlement, keeps his voice steady as he recites the final checklist while Dr. Mei Chen, the mission's quantum physicist, watches for fluctuations in the wormhole's Casimir shielding. Then there's Javier Ruiz, the ex-combat pilot whose job isn't to fly the ship, it's to override the systems if spacetime metrics suddenly spiral toward collapse. Behind them, the Odyssey's spine bristles with fail-safes. Emergency entanglement beacons, fractal redundant navigation AIs, even a prototype chronosync device designed to mitigate time dilation. None of which guarantees survival if the wormhole's geometry buckles. The moment of transit defies all expectation. There's no violent lurch, no Star Trek-style streaking stars. Instead, the viewports fill with a light that isn't light, a kind of inverted glow as the ship crosses the event horizon. Sensors scream warnings as tidal forces twist the hull, but the metamaterials hold. For 3 subjective minutes, the crew watches spacetime itself warp around them, the walls of the tunnel pulsing with strands of blue-shifted quasars, their light stretched into ribbons by the gravitational shear. Then silence. The Odyssey emerges not with a bang, but a whisper, its thrusters automatically stabilizing orbit around Nemesis 3b. The first transmission back to Earth takes 4 years to arrive via laser relay, but the wormhole itself allows real-time data streaming, a loophole in causality that still baffles theorists. When Vance's voice finally crackles through speakers in mission control, the words are simple: throat integrity confirmed, exit coordinates stable, no fanfare, no grand speeches. Just 12 words that rewrite the future. Across the solar system, screens flicker with the first live images from another star. The Odyssey's cameras panning across Nemesis 3b's frost plains, its icy crust glittering under Proxima Centauri's dim red glow. Yet the mission's true triumph is subtle. Buried in the telemetry is proof that the wormhole stayed open long enough for two-way transit. Theoretically, Earth could send reinforcements, supplies, even colonists. But the data also reveals something unnerving: residual quantum signatures suggesting the wormhole remembered its transit, as if spacetime itself had imprinted the Odyssey's passage. Whether that's a feature or a flaw won't be clear until the second mission launches. For now, humanity basks in the quiet awe of having done the impossible, not by brute forcing the cosmos, but by learning to whisper to it in the language of folded space and borrowed time.